Thank you for joining us. My name is Uttara Kumar. I work on the software and AI solutions team here at Xilinx. And I'm very excited to have the opportunity today to introduce you to the Vitis accelerated libraries. At the end of this webinar, we hope that you leave with a good understanding of FPGA accelerated libraries and that you feel ready to take the next step to evaluate Vitis, Vitis libraries, and Xilinx platforms to deploy your applications at the edge, on-premise, or in the cloud. To accomplish that, here's a quick look at the topics that we will cover today, so you know what to expect. Vitis libraries are a key component of the Vitis unified software platform. So we'll begin with a quick recap of what Vitis is. We'll cover the basics, just enough for you to understand where the libraries fit in and to get a sense of the overall design flow. If you haven't already, I do encourage you to view the previous webinars in the AI and Software Acceleration series for a more in-depth introduction to Vitis. We'll then zoom into the Vitis libraries, give you an introduction, discuss the functionality and flexibility they offer, see how these libraries are structured and how you can use them with the help of some examples. We'll then move away from our slides and I'll pass it over to my colleague Frederic to show us a demo walkthrough with the Vitis libraries. Finally, we'll wrap up by pointing you to the Getting Started resources to learn more and start your development. With that, let's dive right in. So what is the Vitis Unified Software Platform? Vitis enables a broad range of developers, including software engineers, algorithm developers, and data scientists, to accelerate their applications and adapt to rapidly evolving algorithms and AI models on Xilinx platforms, at the edge, on-premise, or even in the cloud. It offers a unified design methodology and a unified programming model for developers with little or no prior FPGA expertise. With Vitis, you can target a broad range of Xilinx platforms, starting with Zinc 7000, Zinc UltraScale Plus MPSoC, PCIe-based Alveo accelerator cards, and even Versal ACADs. Now let's zoom into this red block that you see on the slide, labeled Vitis, and understand what are the different components of the software platform that enables you to leverage Xilinx devices without having to program in RTL. Let's start at the very bottom of the stack. The fundamental and minimum requirement for development using Vitis is what we call a Vitis target platform. This is what represents the Xilinx hardware platform that you are deploying algorithms on. Now this could represent an Alveo accelerator card or an embedded platform like the Zinc UltraScale Plus ZCO102 board, or you can absolutely define your own custom platform. On top of this layer lies the Xilinx runtime library, also known as XRT. Now this is really what enables communication between the CPU, which could be an x86 or ARM processor, and the accelerated kernels running on the FPGA. XRT is fundamental to enabling this high level of abstraction design flow in Vitis. On top of these two layers sits the Vitis core tools. This is a complete set of graphical and command line developer tools. This includes Vitis compilers, analyzers, and debuggers to build, analyze, and debug your accelerated algorithms. The core development kit is really what compiles and builds out the FPGA binary. Now under the hood, it invokes Vivado implementation tools, but to a user, it offers a familiar CPU and GPU-like development experience. Now tools, while absolutely necessary, aren't enough. You need libraries for getting started, so you as a developer don't have to reinvent the wheel. At Xilinx, we are spending an enormous amount of effort on developing pre-optimized libraries to kickstart your development and lower the barrier to entry. This is what we'll focus and do a deeper dive on in a bit. At the highest level of abstraction in the development stack is what we call domain-specific development environments. These offer integration with domain-specific frameworks for specialized workloads. Vitis AI is our first domain-specific development environment, optimized for AI inferencing workloads on Xilinx. What you see here is a graphical representation of how the different components of the Vitis software platform fit together to enable algorithm deployment. The Vitis target platform defines the base hardware and software architecture for the Xilinx platform. This includes connectivity IPs for external memory interfaces and also custom I/O interfaces. For Alveo accelerator cards, the Vitis target platform automatically configures the PCIe interfaces that manage communication between the FPGA accelerators and the x86 application code. For Xilinx embedded devices, the Vitis target platform also represents the operating system for the processor on the platform, bootloader and drivers for the platform peripherals, and the root file system. The Xilinx Runtime Library, or XRT, as we saw before, is an open source software interface that facilitates communication between the application code that runs on the CPU and the accelerated kernels deployed on the dynamic region of the platform shown here. XRT runs on the host, which can be an x86 or ARM, and primarily manages downloading the FPGA binaries onto the platform, managing the movement of data between the CPU and FPGA, controlling the execution sequence, and other board management tasks. Now, what the Vitis core tools do is enable the deployment of algorithms onto this predefined Vitis target platform. So the next obvious question is, how do you develop these algorithms that can be compiled by the Vitis tools and eventually deployed on the platform? There are primarily four main steps for accelerating applications with Vitis. The first step is identifying the need for acceleration and establishing your performance goals. To do this, you would profile your application, which can be done using common software profiling tools. This helps you make key decisions and identify which software functions are bottlenecks and need to be offloaded, how much parallelism is needed in your application, and how it should be delivered. Now, establishing performance goals are crucial because that is what drives performance analysis and decision making along the way. For example, a real-time video application could have the hard requirement to process 4K video at 60 frames per second, whereas a data science application could have the soft goal to run about 10x faster than an alternate implementation. It really depends on what you need to accomplish in your application. Once you have identified the performance critical functions and set your performance goals, the next step in the process is designing the accelerated kernels that can be deployed on the FPGA fabric. To do this, you can use performance-optimized Vitis libraries, design custom algorithms in C++ and use compiler directives to steer performance. You can leverage Xilinx-optimized add-on toolboxes for MATLAB and Simulink, and you can also reuse RTL IPs within a Vitis application. The choice here really depends on the algorithm developer. Next, you would build the accelerated kernels, analyze performance, and debug any issues in your application using the Vitis core tools. Now, this is the step where you want to verify functional correctness of the algorithm and validate that your performance goals are met. Now, the initial version of an accelerated application will likely not produce the best possible results. Performance optimization is an iterative process. So by following the design methodology and the guidance offered by the tools, you will be able to iterate through the process and get to the performance you need. Finally, you want to build for deployment onto the hardware. The Vitis compilers build the FPGA binary for the Xilinx platform by running synthesis and implementation. The Vitis environment completely abstracts away the underlying process of synthesis and implementation. However, for complex designs, and if the user wants to, Vitis does offer some control over Vivado through specific options that can be specified in configuration files or from the command line. Now, let's take a closer look at step 2, which is designing the accelerated kernels. We saw on the previous slide that there are different entry points for designing your accelerated kernels, but they broadly fall into two main categories. One, using pre-optimized libraries, which is the easiest way to hit the ground running. And second, designing your own custom accelerators. And you can do this in MATLAB and Simulink, you can use RTL IPs, or you can design them from scratch in C and C++, using compiler directives to steer performance optimizations. Let's focus on the accelerated libraries for the rest of this presentation. Vitis offers an extensive set of performance-optimized libraries that are open source and available to all developers on GitHub. Now, common libraries like math, statistics, linear algebra, and DSP are relevant to a broad range of applications and industries. These are basic algorithmic building blocks. In addition to the common libraries, there are a number of domain-specific libraries as well that are pre-optimized for specific workloads. Examples of these include libraries for vision and image processing, quantitative finance, data analytics and database acceleration, data compression, data security, and with every release, we continue to add on to this list. We have over 400 pre-optimized functions across all the Vitis accelerated libraries available today. One of the benefits of a unified design methodology offered by Vitis is that it also enables the partners in the Xilinx ecosystem to develop accelerated libraries for our customers and to strengthen the overall solution to use Xilinx platforms. The source code for the Vitis accelerated libraries are written in C and C++. This means that you can design algorithms in familiar programming languages with no prior RTL experience. Some of these libraries also offer Python APIs, making them directly callable in Python host applications. Now, some of you might be thinking, if these libraries are written in C and C++, and FPGAs inherently need specialist hardware description languages to program them, how does this work? This is automatically handled by the Vitis Code Development Kit. The Vitis compilers automatically synthesize these libraries into RTL using the high-level synthesis or HLS technology under the hood. No prior FPGA experience is required to use these libraries. They enable a familiar CPU and GPU-like design experience. This means that as a developer, you can work at an application level and focus your domain expertise on algorithm development without worrying about low-level implementation specifics, which are taken care of for you by Vitis. The accelerated libraries are scalable across all Xilinx platforms. You can develop your applications using these optimized libraries and seamlessly deploy across Xilinx platforms at the edge, on-premise, or in the cloud without having to re-implement your application from scratch. Now, fundamentally, what enables this platform-agnostic development in Vitis is the Xilinx runtime library that we briefly discussed earlier. Xilinx runtime library APIs help abstract the application development from the deployment platform itself. This means that you can easily port your algorithms from, for example, an embedded platform to an Alveo accelerator card or vice versa. Vitis libraries offer different levels of abstraction. This gives you the flexibility you need to use them as you wish. At the lowest level are the library primitives or level 1 functions. These are the smallest building blocks in terms of functionality for designing accelerated kernels. For those of you familiar with HLS, you can also think of them as individual HLS functions. Now you can customize and combine multiple level 1 functions together to form a kernel. Next comes the library kernels or level 2 functions. These are designed as individual performance-optimized kernels with the required interfaces for Xilinx runtime library to talk to it from the host. You can combine multiple level 2 functions together to form your end-to-end processing pipeline. You also have the option to build the level 2 kernels using test cases and make files that are provided on GitHub. This is primarily to test functionality in simulation via the software emulation and hardware emulation option in Vitis, and you can also run them directly on supported hardware after building the accelerator using the tools. At the highest level of abstraction is the library API or level 3 functions. These can be directly called from the host application. Essentially, these are pre-compiled FPGA binaries or overlays that are ready to be called from the host via a library API call. The primary use case of level 3 functions is to enable rapid prototyping and evaluation of the performance benefits that Xilinx can bring to your application. You can then, of course, customize and rebuild these level 3 functions with any specific changes required for your own unique applications. In summary, you can use the Vitis libraries as is, as algorithmic building blocks, modify them to suit your specific needs, or use the source code simply as a reference to completely design your own kernels. Choose the flexibility that you need. All Vitis libraries are available for download on GitHub at the link specified here. These libraries are open source under the Apache 2.0 license, which is very permissive. They're all organized using a uniform structure on GitHub. Each library comes with its own comprehensive documentation. This includes a description of functionality, function parameters required, and individual performance estimates as well. The source code for the library functions are organized into different subfolders based on the different levels of abstraction that we just discussed. In addition to the source code, we also offer examples and test cases. These are required to build, emulate, and verify functionality for these libraries. You can also access performance benchmarks, and more importantly, you can access the steps to reproduce these performance benchmarks at your end. Everything that you need to hit the ground running with these libraries is available on GitHub. Now that we've covered the basics around the Vitis libraries, let's introduce you to some examples. Now we'll take a look at 2 domain-specific libraries and 2 common libraries. Computer vision and image processing are great candidates for FPGA acceleration. These applications demand a solution that can meet real-time performance, flexibility to manage a range of different frame resolutions, and adaptable throughput requirements. For example, you might need an algorithm that processes a 1080p video at 60 frames per second and also required to process a 4K video at 60 frames per second, while also being power efficient for both edge and data center deployments. The Vitis Vision library offers FPGA accelerated versions of the familiar and standard OpenCV libraries. They also offer the flexibility to meet the adaptable throughput requirements of your vision systems by processing multiple pixels per clock. Most functions support a maximum of 4K resolution and have been optimized for performance and resource utilization on Xilinx platforms. The accelerated functions include geometric transforms, image statistics, feature detection and classifiers, and also motion analysis and tracking functions, including Kalman filters, stereo disparity, optical flow, and many others. Today we have over 80 optimized functions in this library, and this list continues to grow. View the complete list on GitHub. So at a high level, what is the general flow for designing an accelerated kernel using the Vitis Vision library? First, you would copy the image data into an XFCV mat object. Now, XFCV-mat is a template class that serves as a container for storing image data and its attributes in physically contiguous memory. This enables you to achieve best possible performance. Next, you would call the accelerated functions from the Vitis vision library. All of these are defined in the XFCV namespace. For example, here, the XFCV resize is an FPGA accelerated version of the CV resize from OpenCV. XFCV resize requires all the parameters that the OpenCV version requires and some additional parameters like pixel data type and the number of pixels you need to process per cycle, which affects the throughput when implemented. Now, one of the real benefits of using FPGAs is that they're great at streaming data in, processing in parallel, and streaming data out at a very high speed. Remember that going back and forth to memory is expensive, so you can maximize performance here by simply streaming from one operation to the other. In this case, we stream the output of the XFCV resize into the XFCV Gaussian blur to maximize the performance of this kernel. Finally, you would copy the image back into the XFCV mat object to be transferred back to the host. Now, this accelerated kernel is then compiled by the Vitis compiler and deployed on the FPGA fabric. You then call this kernel from the host application via the Xilinx runtime library APIs. As we discussed before, there are several examples of exercising this flow for the level 2 kernels in the library using makefiles. Please do check out the GitHub. Next, let's take a look at the Vitis quantitative finance library. Financial institutions require innovative solutions to meet the increasing compute demands in trading and risk management. Xilinx platforms provide the adaptability, flexibility, and the much-needed computational power to significantly accelerate time to insight while also reducing the total cost of ownership in the data center. So if you're working on financial workloads such as options pricing, modeling, trading, evaluation, and risk management, these are great candidates for FPGA acceleration. The Vitis quantitative finance library offers plug-and-play level 3 APIs with precompiled FPGA binaries to enable rapid evaluation of the acceleration you can achieve on Alveo accelerator cards. Some examples of these APIs include Monte Carlo-based American and European options pricing engines, binomial tree engines, the Heston finite differences and closed form solutions, and others. Now, when you're ready to move beyond evaluation and start accelerating your own custom pipelines, you can access a number of performance-optimized primitives, that is, level 1 and level 2 functions. And you can see a few examples of those on the slide here. For a complete list, again, I encourage you to view the list on GitHub. Let's take a look at an example. The Monte Carlo-based American and European options pricing engine is available as a level 3 function. It has a Python wrapper that enables you to call this directly from your Python host application, as you see the function calls here in bold. This is very similar to calling a native CPU function. Now, when you call the library API, it takes care of the underlying specifics of loading the precompiled FPGA binary onto the platform, which in this case is an Alveo accelerator card, taking care of kernel configuration, transferring data from the host to the card, and then bringing the results back to the host after computations. As you see, again, it's an excellent way to start evaluating the performance benefits that Xilinx platforms can bring to your application. Now, what kind of performance benefits can you expect to see here? What you see here is a performance benchmark that we published for the Monte Carlo-based American and European pricing options. The FPGA accelerated pricing engines are running on the Alveo U250 accelerator card, and their performance is being measured against the equivalent quantlib library calls that were run on a multi-core CPU. Now, the QuantLib is essentially an open source C++ library for quantitative finance. What you see here is that the Monte Carlo European options pricing engine achieved almost a 1500x speedup for warm runs, while 380x speedup for cold runs. Now, a warm run is basically when the pricing engine is already up and running with sufficient memory allocated to handle the request, whereas a cold run is when the pricing engine needs to start up in response to the request. Similarly, the Monte Carlo American options pricing engine achieved a 529x speedup for warm runs and 176x speedup for a cold run against the CPU listed here. All of this using a plug-and-play Level 3 API. Now, moving on from domain-specific libraries, let's take a look at two examples of the accelerated linear algebra libraries. These are common algorithmic building blocks that you would use to build your own FPGA accelerated applications. The first example we'll look at is the Vitis BLAS library. The Vitis BLAS library is a performance-optimized implementation of the standard basic linear algebra subroutines. These are used in a range of different applications like multi-layer perceptrons or MLP, computer vision, and even quantitative finance. The Vitis BLAS library APIs like General Matrix Multiply or GEM and General Matrix Vector Multiply or GEMV are available as precompiled accelerators with C, C++, and Python function interfaces. Again, this enables you to drop and replace CPU and GPU-based BLAS API calls with the Vitis BLAS API for rapid prototyping and performance evaluation. In addition, the library also includes performance-optimized primitives that aid in customizing, modifying, or building your own kernels. These include FPGA accelerated versions of dot products, Euclidean norm, min, max, scalar vector product, and others. You can view the complete list on GitHub. The Vitis solver library, on the other hand, is a collection of FPGA accelerated matrix decomposition, linear, and eigenvalue solvers. These are essentially performance-optimized versions of algorithms in the LAPACK library, or the Linear Algebra Package Library. In combination with the Vitis BLAS library, these can be used to accelerate complex algorithms. For example, the finite differences method in the quantitative finance library we just saw uses an accelerated tridiagonal solver and a vector matrix multiplication from the Vitis BLAS library. Other performance-optimized primitives, or basically level 1 and level 2 functions in this library include matrix inverse, QR decomposition, SVD decomposition, Jacobian eigenvalue solvers, and others that are fundamental building blocks in a range of different applications like radar, LiDAR, computer vision, DSP, and controls, among others. Today, we have a total of 9 libraries available on GitHub. These include the database library, the data compression library, security library, DSP library, and also a common utilities library. Now, in the interest of time, we won't be able to cover all of them, but we do encourage you to check out the breadth of functionality available on the GitHub page, and also check out the library documentation that's linked here. With that, it's now time to dive into a demo walkthrough to see these libraries in action and learn how you can get started. And for that, I'm going to now pass it over to my colleague Frederic, Product Manager in the Software and AI Solutions team here at Xilinx.
Thanks, Petra, for your presentation. As we just saw, the Vitis accelerated libraries do cover a wide range of application domains, database, quantitative finance, data compression, etc. Accessing the content is as simple as browsing to the Vitis libraries on github.com. Here, I download and expand the repository via the git clone command. All these libraries are written in C++ as templated functions. They're grouped together under a single repository, and they all follow a common file arrangement with different levels that I'm going to discuss. As was explained, there are 3 levels of granularity from 1 to lowest to 3, the most complete. The level 1 shows all the individual functions, one function at a time per directory. They can all be compiled independently with the Xilinx parallel C compiler, HLS. HLS stands for High-Level Synthesis. At level 1, you can focus on tuning the code of the function itself, and the makefiles allows you to interact with the Xilinx parallel C compiler HLS, as we'll discuss in a minute. Level 2 focuses on the full execution model that involves the host CPU program calling the accelerate function to be executed onto the FPGA. At that level, you can emulate the FPGA accelerator alongside the host program, meaning that you can execute the host program calling a model, and you can also generate a binary for the accelerator to run the full example, host plus accelerator, onto hardware and without emulation. Level 3 is about advanced design that most often combine multiple base functions into a series to achieve the desired functionality. For this walkthrough, I'm going to focus on the vision example and look at their level 1, 2, and 3. So I navigate to the vision directory to run one of these examples from the build directory. Here I am picking the Harris filter. There is a data directory with test image and a build directory where you will find a makefile that enables all the possible actions. As you can see here for this Harris filter example, you can run csim, which represents a simple C emulation of the library. This is a functional simulation that only involves GCC. No processing on the Vitis part is tested here. The test vectors are driven by the file with the _tb in its name, tb standing for testbench. csynth for parallel C synthesis with HLS, meaning that the Vitis compiler will this time analyze the function to map it onto a representation that can be implemented onto the Xilinx device or platform that you pass as an argument to the makefile. CoSim is the second level of simulation. Unlike csim, with this option, the model simulated for the function is the synthesis result of the C parallel compiler. This is obviously quite important as you can make sure the compiled file do represent the functionality correctly. The tests are the same as the one running on the test bench file as we discussed, but this time it's the function as synthesized by the Xilinx tools that would be tested. Now I navigate to an example, this Harris filter to run make. I first run make without options to see the choices and then run for csim, which is again the functional simulation. I also specify a target device. Here I'm interested in the Alveo U200 acceleration card. Once I run, the tool executes the test bench file that wraps around the function on the test. Here, the Harris filter. csim is usually quick as it's pure C-based simulation. Now switching to level 2. At this level, it's not just the accelerated function itself that we test, it's also the host code running on the server. Since this level involves running an actual hardware accelerator, for example an Alveo card, I connected to Nimbix. Nimbix is a cloud service provider that offers a Vitis preset environment and offers a choice of different servers, some of them pre-fitted with Alveo cards. Here I'm selecting the Alveo U200. I already visited Nimbix in some previous sessions, for the Vitis libraries already installed on my /data directory that Nimbix retains across my different sessions. In L2, the host portion of the application is involved. It's through OpenCL API that these functions communicate with the accelerator on the Alveo card. and I can run both emulation at the software level and hardware level. When making a change to a design, emulation gives you a quicker iteration compared to building to actual hardware and running on the accelerator itself. Emulation is also useful for its specific debugging features. Here I already pre-compiled an edge detection function called Canny on a different directory. As you can see here, all the files were created already from a prior compilation. All I have to do is to rerun the actual binaries. So here it goes. Now I can review the resulting image using the server's file browser utility. And here I'm quickly inspecting the input file and comparing to the processed output from running on the board. At level 3, multiple functions are grouped together to build a processing pipeline and implement a full application onto the accelerator. For this example, I selected the benchmark application called X plus ML, meaning Xilinx IP plus machine learning. This is an image pre-processing example that helps prepare the incoming images to a formatted dataset. This is because a machine learning application could be receiving data from heterogeneous sources and image formats and sizes. These images need to be transformed to a known format and size for downstream analysis before being passed to the model. This example shows how various Xilinx Vitis Vision Accelerated Library function can be used to accelerate pre-processing of input images before feeding them into a deep neural network accelerator. The specific application shows how pre-processing for GoogleNet_v1 can be accelerated, which involves resizing the input image to 224 by 224, followed by a mean subtraction. Running the application is like what we saw on level 2. Same options in the makefile, and here on Nimbix, I am showing the command build the design for hardware. The full build takes about 2 hours. The performance numbers are shown at the README of the example. It's included in the repo as well. The compilation to hardware takes a longer time. The tool will first compile to C++ kernel. Thanks for your attention. This was a walkthrough of the Vitis library. They are level 3. Shows how to emulate and run these libraries onto the Alveo card via Nimbix. I turn it back to you, and I will stay around for questions. Thank you.
Thank you very much, Frederic. Let's now try to wrap up real quick and get to the Q&A section of this webinar. Now today we specifically focused on the Vitis accelerated libraries developed by Xilinx. But there are a number of partners in the Xilinx ecosystem who have developed their own FPGA accelerated libraries and applications for a range of different use cases, including genomic sequencing, machine learning, and others. Feel free to explore the partner solutions available today. You can find them on the link here. This will also give you another peek into the kind of workloads that will hugely benefit from acceleration on Xilinx platforms. Now we hope you're excited and ready to take the next step to start development with Vitis and Vitis libraries. The Vitis co-development kit and libraries are available to all developers completely free. You can download Vitis from the Xilinx download page and the Vitis libraries from GitHub. The Getting Started tab on the Vitis product page linked here has a lot of great information in one place. This includes links to download the runtime library, the Vitis target platforms, and even access to training courses that are available today. This is all you would need to start your development with Vitis. Let's talk about the developer resources available. The Xilinx developer site, located at developer.xilinx.com, is a one-stop shop for all developers to access technical articles, tutorials, and examples for getting started. Now, these are all curated by technical experts at Xilinx. In addition to this, there are also bite-sized tutorials available on GitHub, linked on the slide here, and these offer a step-by-step introduction to Vitis.